When you think before you speak, reread your statements before you click post, or sleep over it for a night before deciding to buy that item from an online store, you are unconsciously practicing the concept of probability. This is at least true for logical people. Acknowledging the role of probability in their lives makes them logical. Probability is a quantitative variable. An event E will have no chance of happening at all if, for example, its probability is 0. And there is a 100% chance it will happen if its probability is 1. So that's what we see here in this particular statement. The possible values of probability can never be below 0, nor be greater than 1, but it can be anything in between those values. Events that cannot both happen simultaneously, like getting a head and a tail at the same time after tossing a coin, are known as mutually exclusive events. To compute for the probability that either mutually exclusive events happen, we simply add their individual probabilities. For example, the probability that a coin lands on its head is 1/2, or 0.5. This is also the same probability that the coin will land on its tail. The probability that the same coin lands on its tail or on its head is the sum of these two probabilities. That means 0.5 plus 0.5, or 1. Think about it. If you guessed that a coin toss will end up with a tail or a head, then you will always have the correct guess. Here are some symbols that will be recurring in our discussions involving probability. So we have here the brackets, used as a shorthand for the phrase the event, okay, because probabilities talk about the probabilities of events happening. And then this symbol here, looks like a letter U, stands for union, or in English, or. So A union B means A or B. And in these illustrations, we have here what we call as Venn diagrams. We can see here in Venn diagram A that events A and B are exclusive of each other. There's nothing in common between them. So the union of A and B, meaning to say A or B happening, will be shading both of these. And then here we have a non-mutually exclusive event, meaning to say there's an overlap between the two events A and B. Here we have a symbol that's like it looks like the opposite of union. This is intersection. So this is A intersection B. And in English, it stands for the word and. So A and B occurring simultaneously. And that means in the Venn diagram shown here, A and B occurring simultaneously is the overlap between the two events. And then here we have a symbol, A, and then there's a bar on top. That means that we are talking here about the complement of the event A. So the complement of the event A is actually the probability of the event that A does not happen or occur. So, in a sense, we can say that the probability that the complement of A happens is just equal to 1 minus the probability that A happens. So here is a Venn diagram representing the complement of A. So it's outside the event A. So here we have an example on the probability of complement of an event. So let events A and C be defined such that A is the event when X is less than 90, and C is the event when X is greater than or equal to 90. And let's say we know that the probability of A happening is 0.7. Then what is C equal to? Notice that C is exactly the opposite of A. It's when X is greater than or equal to 90, the opposite of X being less than 90. Then we can therefore say that C is really just the complement of A. Okay? And the probability of the complement of A happening, or C happening, so they're equal, is equal to 1 minus the probability of A happening. That means 1 minus 0.7 or 0.3. So this is what C is equal to. Another thing that we need to consider about events is their independence from each other. Two events are independent if the occurring of the first event does not have any bearing at all with the occurring of the second event. So two events A and B are independent if the probability of A and B occurring is equal to the product of the probability of A and probability of B. So consider the following events. Event A is when the mother's diastolic blood pressure is greater than or equal to 90. And event B is the event where the father's diastolic blood pressure is also greater than or equal to 90. Suppose we know that the probability of A is 0.1 and that the probability of B is 0.2. What can we say about the probability of A and B happening? Well, this is quite a tricky question because first and foremost, you need the information of whether events A and B are actually independent. And the problem doesn't say that. So therefore, we cannot answer this unless we know that these two events are independent. So let's consider the same events. Suppose we know that the probability of A is 0.1 and the probability of B is 0.2. What can we say about the probability of A and the probability of B happening if now we are given the condition they are independent? So in order to solve that, then we simply have to multiply the probability of A to that of the probability of B. So that gives us 0.1 times 0.2 or 0.02. Here is a visual representation of our problem. The probability that the father and the mother both have a diastolic blood pressure equal or above 90 is actually just the overlap of each of their probabilities that they will have a diastolic blood pressure equal or above 90. So this is that probability we're talking about, the overlap. Here's another example. Consider all possible diastolic blood pressure measurements from a mother and her firstborn child. So let's say event A is when the mother's diastolic blood pressure is above or equal to 90. And event B is when the firstborn child's diastolic blood pressure is above or equal to 90. Suppose that the probability that events A and B happening is 0.05 and that the probability of event A is 0.1 and the probability of event B is 0.2. What can we say about events A and B? Okay, well, first and foremost, the probability of events A and B happening, we know that already, it's 0.05. And the probability of A only happening is 0.1 and B only happening is 0.2. Now, we can try some tests on independence here. Let's try multiplying the probability of A with that of the probability of B. The probability of A is 0.1 and the probability of B is 0.2. The answer is 0.02. Now, this probability is only true if they are independent events. But we see here as given that indeed, when they both happen together, the probability is not this. Meaning to say, we can say that the probability that the mother has a DBP above or equal to 90 and the probability of and the event that the first child has a DBP above or equal to 80, these two events are not independent. Does that make sense? Well, it will make sense if you think about it this way, that if the mother's lifestyle is unhealthy, causing her to have high blood pressure or a DBP greater than or equal to 90, most likely she will influence what her firstborn child's lifestyle will be, causing also the DBP of that child to be that of a hypertensive child above or equal to 80. So, two events A and B are dependent if the probability of A and B happening is not equal to the product of the probability of A and B. So here's another example. Suppose two doctors A and B test all patients coming into a clinic for syphilis. Let A plus be the event when Dr. A makes a positive diagnosis, and B plus be the event when the Dr. B makes a positive diagnosis. Suppose Dr. A diagnoses 10% of all patients as positive, and Dr. B diagnoses 17% of all patients as positive, and both doctors diagnose 8% of all patients as positive. Are events A plus and B plus independent? So we test this with the product rule again. So we have first probability of A plus and B plus happening. That will be equal to the product of the probability of A plus and B plus. So let's test this. The probability that Dr. A will make a positive diagnosis is 10% or 0.1. And we multiply this with the with a probability when Dr. B makes a positive diagnosis, and that's 17% or 0.17. If we multiply these, the answer will be 0.017 or 1.7%. And that is very different from the 8% given here when both of them will diagnose a patient as positive. What does this mean? This means that Dr. A diagnosing a patient as positive is dependent on Dr. B diagnosing the patient as positive. That means there has to be some relationship, right? If you are being diagnosed by Dr. A as positive and you go to Dr. B, there will be a very high chance that Dr. B will also diagnose you as positive for this particular disease. So here's the multiplication law of probability. The probability of, if events A sub 1 up to A sub k are mutually independent events, if they are independent, then the probability of A sub 1 and A sub 2 dash dot 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 and A sub k will happen should be equal to the products of their individual probabilities. That was not the case with our example here. So this example, the events were dependent, not independent. So here we talk about mutually and non-mutually exclusive events. We go back to this. Okay. The probability of an event E denoted by PRE always satisfies this. We already know that. Okay. If outcomes A and B are two events that cannot both happen at the same time, then the probability of A or B occurring should be equal to the sum of them both occurring. We already tackled that a while ago. What if we talk about non-mutually exclusive events? An example of a non-mutually exclusive event would be this. Picking a card out of a deck of cards, what is the probability of that card being red and a diamond? Or a diamond. Okay? Again, what is the probability of that card being red or a diamond? Now, in that particular case, the two events being red or being diamond are not mutually exclusive because they can both happen at the same time. You can pick a card that's both red and a diamond. So, here's a more general formula for mutually exclusive events and non-mutually exclusive events. If A and B are any events, the probability that A or B happening will be equal to the probability of A plus the probability of B minus the probability of A and B happening. So we have added this somehow, this last portion. If you notice in our first example on mutually exclusive events, we only stopped here. We only considered these two. But now we have to consider both of them happening because they might not be mutually exclusive. So this one is the law of addition or the addition law of probability, also known as the OR law. And again, in this illustration, in this Venn diagram, we can see events A and B are not mutually exclusive. They can happen together at the same time. So here's another example. Suppose two doctors, A and B, test all patients coming into a clinic for syphilis. So same scenario. Suppose a patient is referred for further lab tests if either Dr. A or B makes a positive diagnosis. Okay? What is the probability that the patient will be referred for further lab tests? So that means that's the probability when Dr. A makes a positive diagnosis this time or Dr. B makes a positive diagnosis. Okay? So, what will be the formula here? So, this will be now the probability that Dr. A makes a positive diagnosis plus the probability that Dr. B makes a positive diagnosis. Now, are these mutually exclusive events? The answer is they're not. So, we have to subtract, therefore, the probability when Dr. A and Dr. B makes a positive diagnosis. So, our equation will now look like this. The probability that Dr. A makes a positive diagnosis plus probability that Dr. B makes a positive diagnosis minus when both of them make a positive diagnosis. Sorry, this is supposed to be 0.08. This one is 10%, so okay, that's correct. And then we have 17%. Okay, so what will be our equation here? We now have 0.1 plus 0.17. That's 0.27 minus 0.08. So there is a 0.19 or 19% probability that the patient will be referred for further lab tests. So here are special cases of the addition law of probability. So this will look very familiar to you. Okay, so here we have the addition law or law, and then we have to consider here independent events. And then if they are mutually exclusive, then we do not need to subtract the PR, A, and B here anymore. We don't need that because there's no chance of them happening together. So this formula will do if they are mutually exclusive. If they are independent events, then we have to consider adding back this portion. So that's what we see here. Okay? Or you can have this formula. So these two formulas are the same. Okay? Maybe I'll leave it up to you to figure out how this one is the same as this. Clue. 1 minus PRA is actually the probability of the complement of A, as you can see in this Venn diagram. So here we have another example. Two events. Event A, when the mother's diastolic blood pressure is greater than or equal to 90, and event B, when the father's diastolic blood pressure is greater than or equal to 90. Suppose the probability of event A is 0.1 and the probability of event B is 0.2. Assume that A and B are independent events. Suppose a hypertensive household is a household where either the mother or the father is hypertensive, what is the probability of a hypertensive household? Okay, so that will be the probability of a, let's just say, a hypertensive household is when the probability of, is when the events A or B happen, right? That's when the probability when the mother is hypertensive or when the father is hypertensive. And these are independent events, so our formula will be probability of A plus probability of B minus the probability when both of them happen together. So that gives us 0.1 plus 0.2 minus, when the probability that A and B happen together, minus 0.1 times 0.2. So this gives us 0.3 minus 0.1 times 0.2 is 0.02. And the answer here will be 28% or 0.28. That's the probability that a household will be hypertensive if we define that to be whether the mother or the father are hypertensive, and these are independent events. So I hope you will take time in understanding the concepts presented here, and thank you for listening.